Hello, this is just a quick overview video of the Cartesian space controller, a hybrid force position Cartesian space controller with this Dynamixel OpenManipulator-X robot arm. So just to go over the hardware, this is the Dynamixel OpenManipulator-X robot arm. I believe it's a kit that comes with 4 axes of rotation, and then the 5th axis is the gripper itself. Also included in the kit is the UT-DUT power hub board, which is an on and off switch, and a board that takes in power from your wall wart, your transformer, and a USB connection which goes to your computer, and then the motor connections which are serial going through talking to each X series Dynamixel motor. In addition to that, we have a custom force sensing end effector. This is a 3D printed base that fits nice and snugly in the closed gripper. We also have a inline strain gauge combined with a spring-loaded slip joint to help dampen out some of the forces on the control system. And there's a roller on the tip for doing force control in one axis, and then position control, changing the position in another axis. Right now we're going to demo force on one axis, maintaining position in the other axes. The strain gauge goes to a Wheatstone bridge chip and an Arduino, and just a liquid crystal display to show the force output. So you can see I can push on that and it changes the force value. We also are using this to data log for doing some performance characterization and graphing and stuff like that for a project report. On the software side, like I said, we have a Cartesian controller that's running on ROS. We have a batch script file here, which we're going to use to demo the project. We got our terminal for running the ROS core, and then we have the 4 nodes that make up the control system, which is the axis node, control node, trajectory node, and the host node. And then the host node receives commands for Cartesian position moves or apply force moves. So the go to pause command is for the Cartesian moves. We have our X, Y, our Z value, T is the end effector angle, and speed. This should be renamed. This is actually the duration of time the motion path takes to complete. So it's not really a speed, it's like a motion path time parameter. You could use it as a proxy for speed, though it's just kind of inverted, if you know what I mean. So what's going to happen here is we have our first motion command, which is a preposition. We have a sleep for 5 seconds just to let things stabilize, and then we move in at a value of -0.18 in the X. In the X is this direction, and this is just a scrap of countertop material, just a smooth, hard surface for the robot to push into, screwed to the wall. So we have our preposition right next to the board, and then we have our first apply force command, which is has the axis and the magnitude parameters. Axis is -x, which is putting the force into the board, and the magnitude is 2 newtons. We wait, then we go to 4, then 6, then back to 0 before prepositioning at a different height. This is a little bit higher up for the robot arm, positioning into the board, and then the same sweep of 2, 4, 6, and 0 magnitude force commands, and then prepositioning away from the wall, or post position, I guess you could call it. It's worth noting too that there's a ramping functions built into these force commands so that it's not an abrupt change. It takes 2 seconds to ramp from the current value to the commanded value. Okay, so to launch this, we're going to create a terminal in our scripts directory, and this is our src Dynamixel lib scripts directory. And we are going to send the troubleshoot 4, which is my kind of batch script file name. It's a bad name for batch script file, I suppose, but that's what I got. So we're going to go ahead and start this control system. As it's moving, I will describe what it's doing, and I will try to show you the force sensor readouts there as well. So here we go. As things come up. Oh, forgot one thing. Very important thing. I'm going to close all this. Start my terminal again, and I forgot to turn the motor's power on. There we go. Okay. Looks like everything's starting up okay. So the first motion for the robot is a rough preposition. And then a closer preposition right up to the wall. Now we should be getting our ramped force command. There it goes into the wall. And our readout is 2.2 newtons. And here comes our next set point of 4. We're reading 5.5. So there's actually quite a bit of error in this posture. Next ramping point is 6 newtons, and we're reading 7.5 roughly. And then we'll be ramping down to 0. You can see the system relax, and it will go to the next preposition point, slightly elevated in the Z. And closer to the wall is the next position. That's just the Cartesian moves. And now we're switching into the hybrid force position control, where we are maintaining the Y, Z, and end effector angle control loops in Cartesian space, and we're applying the force in the negative X axis, which is into the board. So this is our 4 Newton set point. We're reading 3.6, and our next one is 6 Newtons, and we're reading 5.65 roughly newtons, and you'll see relax as it ramps back down to 0, and then pull away from the wall. A little oscillation in the control system there. All right, I think the only other thing that I could show here is the ramping position. This is just for data logging purposes. The logs, you can see, here's the logs where we have the force ramping going from our 6 Newton set point, ramping down to 0, our ramp percentage, and then we have the Cartesian position logged to. You can see that there's a little bit of a difference in the X value as the spring gets compressed and pushed into the wall. This will be better represented in the project report with graphs and a more detailed description. Thanks for watching.